So the first time I heard the term terminal velocity, I, in my childish brain, thought it meant the speed at which you die. Because, right, terminal illness, yeah, it's not that, it turns out. So terminal velocity is just the maximum velocity you can attain while moving through a fluid. Okay, so usually we're talking about that in the case of something falling. The fluid you're falling through is air, and at some point you can't fall any faster, because the faster you fall, the greater the drag force is that's pressing up on you, counteracting gravity pulling you down. Okay, so terminal velocity is the fastest speed you can attain while moving through a fluid. And as your speed increases, let's just talk about while you're falling. As your speed increases, the force of drag due to the air you're moving through also increases. So as speed increases, the force of drag increases. And eventually, the force of drag and the force of gravity will be equal. So the force of gravity on you depends on your mass. And that's it. That's all it depends on. The force of drag depends on other things. So it depends on your surface area, it depends on the density of the fluid you're moving through, and it depends on your speed. And so as your speed increases, the force of gravity is not increasing because your mass hasn't changed, but the force of drag is increasing. And so eventually those two things are going to balance each other out. And when those two things balance out, then your acceleration becomes zero. So gravity had you speeding up and speeding up and speeding up, but the amount that you're speeding up is decreasing as drag increases. So maybe you were accelerating at 9.8 meters per second squared, but as you speed up, then your acceleration decreases to 9.5 and then 9, and then eventually it's going to make it to 0. So terminal velocity is going to depend on a number of things. It's going to depend on the thing that's falling. The greater the force of gravity on the thing that's falling, the faster it's going to be able to go before drag will get big enough to make the acceleration 0. So the first thing is it depends on the object's mass. Okay? And in brackets we're going to put the force of gravity, because that's what it's really about. The second thing it depends on is the surface area of the object. So if you are at all familiar with skydiving, when you jump out of a plane, they ask you to assume a certain position. And I'm going to try and draw these here. They ask you to spread yourself out something like this. Okay, so that you're falling in a spread-eagled position. And that increases your surface area and gives you a little bit more control over your speed. They do not ask you to jump out of the plane like this, because the surface area that is in contact with the air is just that much. And so the surface area being so small means that the drag force takes a very long time to equal out gravity. And so you can speed up way more if you just go head down straight to the ground. And they don't really want you to do that because you'll lose control, you might black out, who knows. So they want you to increase your surface area because that increases the drag force on you and will decrease your terminal velocity. Right? You won't be able to go as fast if you're spread out like that. And the third thing is density. Okay? So this has to do with the density of the fluid mostly that you're falling through. So if you're falling through the air, you will have a different terminal velocity than if you're falling through water or, I don't know, Jell-O. Can you fall through Jell-O? I don't know. But the density of the fluid is going to change the drag force. So if you have a very dense fluid, then the drag force is going to push up on you a lot harder than if you're falling through something with little density. So if you're jumping, say, from the stratosphere where the air is very, very thin, you're going to be able to speed up a lot more up there than you are when you're closer to the ground, where the air is a little bit more dense than in the upper stratosphere. So when the terminal velocity is very high, the force of drag can be found with this formula. Fd, or the force of drag, is equal to the coefficient of drag times v squared, or times the velocity squared. Okay? Now, the coefficient of drag, it encapsulates this whole density and surface area thing. Okay, so don't think that, oh, you didn't put surface area or density in there. We did, it's just in the coefficient of drag. So the coefficient of drag tells you about the fluid that you're falling through, and it also tells you about the surface area of the object itself. Okay, this is only when terminal velocity is very high. So when terminal velocity is quite low, let's say if you drop a balloon, it does not speed up very much. This formula doesn't work very well for that. Okay, so we're only talking about when you're falling at a very high speed. Skydiving is a great example, dropping something off a building, that type of thing. Let's do an example here. What is the terminal velocity of a 3 kilogram object falling through the air, where air resistance can be found by the force of drag equals 0.1 v squared? So it gave you that whole formula for the force of drag, but really what this piece of the question is telling you is just this is the coefficient of drag that we're using. Okay, so this is a 3 kilogram object, it's falling through the air, and the coefficient of drag is 0.1. So what we're really trying to solve for is what is v, right? So let's put that over here. V equals what? And specifically, we're looking for what's v when the force of drag and the force of gravity are equal. Okay, so whenever you see terminal velocity, what this actually means is we're looking for where the force of drag is equal to the force of gravity. Okay, so what that means is when we're going to use the force of drag equals 0.1 v squared, what we can do here is substitute in, instead of the force of drag, we can substitute in the force of gravity. Okay? That's what we're going to do. Force of gravity is now 0.1 v squared. And again, we can do that because the force of drag equals the force of gravity at terminal velocity. You're going to be asked other questions where you have not reached terminal velocity. It's about drag, so it's a problem-solving question involving drag, not necessarily involving terminal velocity. So when you're practicing and when you're solving problems with things falling, then make sure that the question you're looking at is actually referring to terminal velocity before you plug in this FD equals FG thing. Okay, that's only for terminal velocity. So we know that the force of gravity is mass times 9.8 equals 0.1 v squared. So we know that m is 3 kilograms. We know that g is 9.8 meters per second squared. We're given the coefficient of drag, and so we can solve for v. Now I'm going to rearrange this first, then plug in the numbers. So v, I want to divide by 0.1, and then I want to square root it, right? This is v squared. I do not want v squared. I want just v. And so I'm going to first of all divide by 0.1. So mg divided by 0.1 equals v squared. And then I want to square root everything because I'm trying to solve for v. So v equals the square root. This should have vector symbols on them. V is the square root of mg over 0.1. That's our terminal velocity formula. Now I'm going to plug in the numbers. V equals the square root of 3 kilograms times 9.8 meters per second squared divided by 0.1. And when I do that square rooting, I get 17 meters per second. This is a vector, and so we should say down at the end, even though it is quite obvious that you are falling down. Our final example here does not talk about terminal velocity. What is the velocity of a 4 kilogram object falling through the air if air resistance can be found by Fd equals 0.2 v squared and it has an acceleration of 4.1 meters per second squared down? So it has an acceleration. That means this is not terminal velocity. Terminal velocity means zero acceleration. And so what we are trying to figure out is what is the velocity? We know the mass is 4 kilograms. We know the coefficient of drag is 0.2. We know the acceleration is 4.1 meters per second squared. And we're trying to find out velocity. So we are going to get velocity from this formula over here. We do not know the force of drag, right? So we can't just plug in the force of drag there and solve for v. We're going to have to get it another way. We are also given total acceleration, and that gives you a clue that you're going to use F net equals ma. Because with a falling object like this, it's experiencing the force of gravity and it's experiencing the force of drag. And I've made the force of drag negative. So what I have said here is that up is negative and down is positive, which is not normally how we do this, but in this case, to me, that makes sense to make positive the downward thing, because that is what the acceleration is doing. Okay, so that's my choice. You can do it the opposite way if you want, and it will work out fine. Your answer will just be negative in the end. So, well, no, it won't be negative. Force of gravity is mg. Force of drag is 0.2 v squared. And then we've got ma on the other side. And we're trying to get the velocity by itself. Okay, so we did a similar thing to this in the previous video, where I'm going to add 0.2 v squared to the right side, subtract ma, so that I have the v on the right side, but it's positive. It's just easier to work with. You don't have to do that. Again, you can do the algebra differently if you desire. So we have mg minus ma is equal to 0.2 v squared. Then I'll divide by 0.2. So mg minus ma divided by 0.2. And then I'm just going to square root this thing right away as well, because I know I need to do that as my last algebra step to get the v by itself. And so let's put in the numbers here. The square root of 4 kilograms times 9.8 meters per second squared minus 4 kilograms times 4.1 meters per second squared. And we're going to divide that by 0.2. And when we do all of that, we get v, or the speed it is going when it hits 4.1 meters per second squared, is 11 meters per second down. Now, you might have noticed that this phrase up here, the top line has a common factor, 4 times 9.8 minus 4 times 4.1. And you are totally right that you can combine those two things, and so it ends up being 4 times 9.8 minus 4.1. Okay, that's totally valid as well if you like doing that sort of factoring stuff in math.